Everyone. Carbocation chemistry part 5. It is all about problems on stability of carbocation. If we want to discuss problems on stability of carbocation, we should have proper idea what are the factors based on which we can decide the stability of carbocation, which I have discussed in part 3 and also in part 4, that is the non-classical carbocation. There also we have seen a different type of carbocation and their stability it's completely because of some other reason, not like normal carbocations, that is classical carbocations. Fine. So based on all these factors that you will get in part 3 and part 4, and for which click on the link, that is a playlist link right now on the top right corner. Okay, so let's start. Here we have the first problem, rank the relative stability most to least. The first one, there is CC double bond adjacent to C plus, that means it is allylic in nature. The second one is 2 degree. Both sides there is carbon, that means 2 CC bonds are present. I mean to say, if you consider the middle one C plus, there are 2 carbon atoms attached to it and only one. So this is 2 degree and this is 1 degree. Okay, and the first one, it is correct that CC double bond is present, but it is also, that is whether it is 2 degree or 1 degree, this is also 1 degree. Fine. Now if we consider only this inductive effect, then 2 degree we know it is more stable compared to 1 degree. But we also have to remember the other factor, which is resonance, which is present only in option the first molecule. So that is why the correct order of stability, this will be the first one. I am giving number here. Suppose this is 1, this is 2, this is 3. So 3 will be maximum stable. After that this 2 degree and then it is 1 degree. So though it is 2 degree, but resonance factor will dominate, will be predominating factor. So that is why this is the correct stability order. Now come to the second one. Here the first molecule, the carbon, it is attached to 3 more carbons. So this is 3 degree, this is 3 degree and this is also 3 degree, right? So based on whether it is 2 degree, 3 degree, 1 degree, we cannot decide anything. Next thing what you will see, what is the type of substituents that are attached to this carbocation. In the middle one, that is number 2, we have 3 methyl groups. In the right hand side we have 2 phenyl groups, 1 methyl, and in the first one 2 methyl groups, 1 phenyl. So here tertiary carbocation, basically all are tertiary, with more resonance factor which is coming from this phenyl ring, that will be maximum stable. After that this one which is having 2 methyl group and 1 phenyl, and the last one that is with 3 methyl groups, this is the least stable. So this is the stability order, most to least. Which one among the following carbocation has the longest half-life? Now this is not directly asking which is maximum stable, but it is asking indirectly which is having longest half-life. That means which is most stable, because when half-life is very high, that means it will be having more stability. Now which one is most stable, that you have to find. If we look at the structures carefully in these 4 options A, B, C, D, you will see the common format is R3C plus. That is 3 similar type of groups are present. In the first case we have the cyclopropane type of ring, in the second case we have phenyl, then cyclohexane, and in the last one CH3. Now if we consider, that is with respect to 3 degree, 2 degree, it is true that all are connected to 3 carbon atoms. So all are basically 3 degree. With respect to that we cannot decide anything. Next you can consider inductive effect, resonance effect. Now compared to that is, in resonance effect is always more important than inductive. So based on that it seems that option B, the second molecule with 3 phenyl ring, that should be maximum stable. But remember, in the non-classical carbocation part, that is in the previous part what we have discussed, the first molecule here cyclopropane, this substituent is attached. When this type of substituent is attached, there is a special kind of stability factor you have to consider. So here you can see this example. This is basically cyclopropane and it is attached to CH2 plus. Simply you consider this carbocation. Basically, if you replace 2 more hydrogen with 2 cyclopropane ring, basically you will get the first carbocation that is given in the question in option A. Okay, so basically CH2 plus attached to cyclopropane. What happens when you have this type of carbocation? So this example we have already seen in the last video. Here these 2,4 bond will be broken and 1,4 bond, that is the newly generated bond, and there is also a minor contributor. So here 2,4 sigma bond is basically stabilizing this carbocation. It is true that it is 1 degree. In this particular example it is 1 degree, but the given one is not 1 degree. But I am trying to focus on the fact that here is this type of cyclopropane ring attached to carbocation, mode will be this stability. And this is a special type of stability for non-classical carbocations. Details you will get in the previous part. You can also click on the link right now, top right corner. This type of resonance is known as bent resonance, and cyclopropyl group, it will stabilize an adjacent positive charge even better than phenyl group. So here this special type of resonance, bent resonance, that is predominating the factor that is resonance stability. So that is why correct option should be the first one. Among the following, which is most stabilized cation? Now this is directly asking which is the most stabilized cation. Come to the first molecule. Here it is 1 degree, and see there are some CC double bonds present and also NH2 group present. Now NH2 group with lone pair, there is a chance that it can show donating, that is resonance, by its plus or effect. Okay, so whether that is applicable or not, that also we have to check. So in this case we have a CC double bond adjacent to it. Now CC double bond, it is, if I simply draw the structure like this, I am drawing a fragment of this molecule, then allyl type of resonance is possible. Okay, now come to the second one. Here CC double bond is far, it is not adjacent, that is not in suitable position so that it can take part in resonance. And this carbocation is, unlike the previous one, 3 degree because it is attached to 3 more carbon. It is 3 degree. Okay, but no CC double bond resonance possible. Come to the next one. Here if we look at the right hand side, this CC double bond, it is having a suitable position so that it can take part in resonance. And also in the right hand side, this CC double bond, that can also take place. One more interesting thing, here this lone pair, that can also be shifted, then this double bond is here. So if I draw the resonance structure after this type of donation, now NH2, it is positively charged, double bond is shifted, this is the ethyl group, and then rest of the position there is no change. So this type of stability is possible from the left hand side. Okay, where plus R effect as well as the CC double bond, everything is present in this resonance. And also if you want to do separately resonance from the right hand side, that is also possible. So here until now whatever we have seen, these 3 species, this is basically maximum stable, right? And what about the last one? The last one, here it is 2 degree because it is attached to 2 carbons both sides, and here this lone pair, though it is present but it is not in a suitable position so that it can show its plus R effect. And also this CC double bond, that will not be able also to show any resonance effect. So keeping all these factors in mind, only in the third one maximum stability possible. Okay, so this is the correct option. Which of the following are correct? So it is basically asking more than one correct answer are correct. Okay, the first one, CH3O CH2 plus. Here this lone pair over oxygen, it is suitably positioned so that it can show resonance, and after resonance the structure will be, now oxygen is positively charged, then double bond, and then CH2. So this is the resonance structure after this type of donation, but that is not present in the second case. So CH3 plus is more stable than the second carbocation. This is obviously correct. So A should be correct. What about the second one? The second one is basically 2-degree carbocation. 2 methyl group attached to CH. So it is 2-degree, but this one is 1-degree. So obviously the first moiety will be more stable, but it is written here less stable. So this is not correct. Third one, allyl group. Basically it is allyl carbocation, CH2 double bond CH. This double bond can be shifted, and the left hand side carbon that will now carry the positive charge. But this type of effect is not possible in the second one. So that is why the first carbocation more stable as it is written here. That is actually correct. So this is fine. This should we should also consider as a correct answer. And the last one, CH2 double bond CH plus, that is more stable than the second one. Now the S character of this carbon, though in both cases it is same number of carbon, but we have a double bond in the first structure, and the S character of this carbon is more if we consider hybridization. You can consider hybridization of the, that is parent compound. Suppose if you consider this is the parent compound CH, okay, I will not write like this, it is basically ethylene. So when you break any CH bond, you get this carbocation, and to break this bond is difficult compared to the parent compound that from which you can generate this one. So here this carbon is sp3, this carbon is sp2, and to break CH bond is difficult. That means this carbocation is not stable. So this is a hybridization before, if you consider you have generated this carbocation from these two parent compounds. But even if you consider hybridization after once that carbocation already formed, then also if you consider hybridization, then also similar logic you can see here, because carbocation it is sp2. That is the second moiety I am talking about. CH2 plus, it is sp2, and CH2 double bond CH plus, it is vinyl cation. Remember, classification of carbocation we have already done. You can also check that video. So once it is formed, now it is sp. So it is sp2. This is sp, and if you consider the parent structure from which it is generated, then this is sp2 and this is sp3. So in both cases, whether you consider the parent compound or not, S character is always high for this first moiety, and it cannot be more stable, because more S character means the carbon is having more electronegativity, so it will destabilize it. Okay, so only A and C, not this one, these two will be correct. Okay, stability order for following cations. Here we have some cations, and the factor that you have to consider here, obviously resonance you can consider, but whether they are aromatic or not, that you can consider. Now if you look at these four, and if you can choose which one is anti-aromatic, and maybe by eliminating some answer or by choosing which one is anti-aromatic or which one is aromatic, you can reach the correct answer. So here this one is anti-aromatic. Why? Because how to choose anti-aromatic or aromatic, I have also made a video based on that there are some specific rules based on which you can easily choose which one is anti-aromatic, non-aromatic or aromatic. These three types are basically present, and for that you can click on the link right now appearing on the screen. So this molecule, basically carbocation, here we have total 4 pi electron. Okay, so 4 pi electron, which is matching with 4n pi rule, where n value is 1. And here the other factors for anti-aromaticity, that is cyclic, conjugation is present, the molecule should be flat, everything, all the factors are present. That means this is anti-aromatic. And if we consider stability, aromatic compounds are more stable obviously than anti, but what about non-aromatic? They remain in between. Aromatic first, then non-aromatic, then anti-aromatic. So if you find any anti-aromatic, it has very high, that is, it is highly, stability is very less. Okay, it is not stable, it is highly unstable. So that is why if you or confirm that this carbocation is anti-aromatic, you can place it in the least position. Okay, so 4 will be having minimum stability, because we have to find stability order, and 4 minimum stability, that is present only in option B. So if you are in hurry and you have to choose the correct option, you can easily choose this option B, when you don't have to look at the other carbocation. But you may not be always lucky enough. Suppose if another option also 4 is present at the least position, because these positions are maximum and these are the least, then obviously you have to check the other carbocations. So this is the anti, and we have reached our conclusion, which is option B. But what about the other one? Why in option B, see here 3 is maximum stable, but why 3 is stable? Here how many pi electrons? 2. Now it is matching with the formula 4n plus 2, where n value is 0 and it is flat, cyclic, conjugated. That means it is aromatic. And aromatic means it will be having maximum stability. And what about 1 and 2? In between 3 and 4 we have 2 and 1 here. So after 3 it is 2. So why 2 is more stable? In 2, here there is a sp3, so there is a break. Full conjugation is not present, but resonance, partial resonance is possible, because of which there is some stability. So it is not aromatic, it is not anti-aromatic. You can say it is non-aromatic. Okay. So 2 is like this, and what about 1? 1 is basically simply benzene ring, but as if one CH bond, it is broken and there is a positive charge. But it has no influence on this type of resonance, which is already, we know this type of resonance is present in benzene ring, and even if there is positive charge, it doesn't matter, because this positive charge is not influencing in this resonance which we see in benzene ring. Okay, it is still aromatic, because 6 pi electrons are present according to 4n plus 2, where n value is 1. It is cyclic, full conjugation present, it is flat. So that is all the factors for aromaticity is present here. So that is why it will also be aromatic. But if you say that this is aromatic, then 3 is also aromatic, then why 3 is more stable? Now you have to see here positive charge is present on which carbon? Here positive charge is present on a carbon which is already part of CC double bond. But in the third case, it is not part of CC double bond. Okay, so that is why 3 will be more stable. Though 1 and 3 both are aromatic, still 3 will be more stable. So which option is correct? It is option B. So I hope now you have some clarity over this type of solving, when you will solve this type of problem. And the more you solve problem, the more clarity you will give. Okay, so thank you for your time.